Okay, for the next one, which is the method of repeating variables and the Buckingham pi theorem. Historically, the first person to write extensively about units and dimension, reasoning in physical relation was Euler in 1765. Euler's ideas were far ahead of his time, as were those of Joseph Fourier, whose 1822 book's analytical theory of it outlined what is now called the principle of dimensional homogeneity, and even developed some similarity rules for heat flow. There were no further significant advantages until Lord Rayleigh's book in 1877, Theory of Sound, which proposed a method of dimension and gave several examples of dimensional analysis. The final breakthrough that established the method as we know it today is generally credited to Buckingham in 1940, whose paper outlined what is now called the Buckingham pi theorem for describing dimensionless parameter. However, it is now known that a Frenchman, Vichy, in 1892, and a Russian, Grabowski, 1911, had independently published paper reporting result equivalent to the pi theorem. Following Buckingham paper, Friedman published a classic book in 1922 outlining the general theory of dimensional analysis. That is what we are going to look into for in this particular part of chapter 7. Okay, dimensional of fluid mechanics properties. You can see on the first column we have quantity. The next, on the middle one, is a symbol, and the third is what represent in terms of the M, L, T, and delta. Okay, this is the I took it from the book of Frank White. Okay, so we have length, which is a symbol of L, and this particular dimension, primary dimension is L, of course. And we also have area, volume, velocity, acceleration, and the rest. Okay. Okay. For the method of repeating variables, there are several steps. Okay. The first step, list the parameters in the problem and count their total number. Okay. Next, list the primary dimension of each of the n parameters. The third, set the reduction J as the number of primary dimension. Then we can calculate the K, the expected number of pi's, okay, which is K equal to n minus J. So K is actually the how many pi's that we have. Step number 4, choose J as the repeating parameters. Step number 5, construct the K pi's and manipulate as necessary. Okay, manipulate means sometimes you can rearrange it. Let's say pi 1 is equal to A over B, but instead of A over B, you can rearrange it to be like B over A, something like that. Okay. Step number 6, write the final functional relationship and check the max, the algebra. Okay. Okay, that is the steps. Okay, to appreciate further more into these steps, I think it is good if we can move into some examples. We have example number 3 here. First, we consider a ball falling in a vacuum. Okay, in a vacuum. Let us pretend that we do not know how much physics concerning falling object. In fact, suppose that all we know is that the instantaneous elevation Z of the ball must be a function of time, and the initial vertical speed, we denote it as omega 0, and the initial elevation is z0, and the gravitational constant is g. That is all we know, suppose, right now. Okay. Okay, that is the representation of the things that we know. Okay, initial height, elevation of the ball, gravity, and the initial vertical speed. And it is our datum, our reference plane. Okay, step number 1. List the parameter in the problem and count their total number n. It is the same steps that given here. Okay, we will follow all the steps. Okay, step number 1, list the parameter in the problem. Okay, from here we know that we have t, omega naught, z naught, g, and also z. So we have 1, 2, 3, 4, 5 items. Okay, we have 1, 2, 3, 4, 5. So n is equal to 5. This is all the parameters n. Okay. Step number 2, list the primary dimension of each of the n parameters. To list down the primary dimension. What is the primary dimension? Length, time, uh, temperature, okay, something like that. Okay, therefore we just take it. Okay, so for the z, we know it is distance, length, so it is L1 to the power of 1, because z here is not a function of anything else. And then t is we know t is t, time, and then omega, sorry, w naught is the initial speed of that item, which is length divided by time. Okay, like meter per second, right? So it should be like this. Then there is length, of course, the initial height, and g is the gravitational acceleration, which is meter per second square. So you put the appropriate dimension according to this dimension analysis. Okay, step number 3, set the reduction j as the number of primary dimension. Calculate k, the expected number of pi. Okay, set reduction j. J is equal to 2. Why it is equal to 2? Okay, the number of primary dimension represented in the problem. Primary dimension, here we only have L and T. Am I right? L, here got L, L, and T. Nothing else, right? We only have 2. Okay, that is our primary dimension. So j is equal to 2. Okay, this is our j lah. 2, 1, 2. And the number of primary dimension represented the problem. Okay, calculate the k, the expected number of pi's. Okay, how many pi's that we are going to get later on. So basically, from the number of primary dimension and the number of total the parameters, then from the differences we can know that the number of pi is 3. Okay, k is equal to 3. K is basically the expected number of pi's. Okay, then choose the repeating parameters. We need to choose 2 repeating parameters since j equal to 2. Okay, because we know that the primary dimension is 2, so we need to choose the repeating parameters. In this case, it is advisable to choose W naught and Z naught as our repeating parameters. Z naught, because the repeating parameters is supposed to be inside this bracket. So we only have 4 options here: T, W naught, Z naught, and G. Okay. So the first repeating variables that we might choose is from W naught, and the next one is Z naught. Why? Why we choose W naught and Z naught? That is because if you look here, W naught, it has both L and T, and Z naught has L. Okay, no problem if you want to choose W naught and T, not a big deal, but it is advisable to choose this and this one. Through several exercise, you will notice there are certain guidelines to actually how to choose these repeating variables. There are certain criteria, and that particular criteria needs a further advancement in knowledge to look into that. Okay. I'm not going to go into that deep in this analysis. Okay. Okay. Step number 5: construct the K pies and manipulate as necessary. Now we combine these repeating parameters into product, which each of the remaining parameters one at a time to create the pies. The first pi is always the dependent pies and is formed with the dependent variables J. Sorry, Z. Okay. Okay, Z, W naught, and Z naught. Okay. And A1, where A1 and B1 are constant component that need to be determined. Okay, from here, A1 and B1 is the things that we are going to obtain. Okay, we apply the primary dimension of step number 2 into the above equation and force the pi to be dimensionless by setting the exponent of each primary dimension to 0. Okay, what it means, it is like this down here. Okay, you set pi 1. Okay, the unit is L and T, so both are, this is our primary dimension, so you just put to the left. Okay, L to the power of 0 and T to the power of 0, and then equal to whatever we have on the right hand side, that up here. Okay, then from here we know that L 1, so we know that Z is L, right? Z is our length to the power of 1, and then W naught here is our speed, which is meter per second, which is L to the power of 1, T to the power of -1. And everything here should be to the power of A1. And similarly for this Z naught, power of B1. Okay, like what we have up here. Okay. Then next part, you can further expand. Since the primary dimension are by definition independent of each other, we equate the exponent of each primary dimension independently. Solve for A1 and B1. What does it mean by independently? Independently means since we know we have deal with time and length, right? We have L and T, right? And therefore we can solve it independently. Time, we have T naught is equal to t to the power of minus a1. This is sorry, this is from what we have. Okay, t to the power of 0 is equal to t to the power of minus 1 times a1. So it is t to the power of minus a1. Okay, that is what we have here. Okay, then we look into this superscript up here, and we know that 0 is equal to minus a1, and therefore we know that a1 is equal to 0. Okay. Again, do the same process for the length. We know that L is equal to L to the power of 1, L to the power of A1, and L to the power of B1. This is from here. Okay, L, this one, this, and this one. So there are 3 L on the right hand side. So you must equate something like this, and you know from here that 0 is equal to 1 plus A1 plus B1. And further you rearrange this, you get B1 is equal to minus 1 minus A1. And you know that A1 is actually equal to 0, and therefore B1 is equal to minus 1. Okay. And from there, you replace what's the value of A1 and B1 into this equation. Okay, A1 is equal to 0 and B1 is equal to minus 1, right? So you know that anything to the power of 0 is equal to 1, and Z naught is the power of minus 1, meaning that you can put it down here. So Z naught, okay, like so. This is what we get for our first pi. Okay, the same procedure from step number 5 is repeated for pi number 2. Okay, just now we look into pi number 1, right? Now we move into pi number 2. Okay, for pi number 2, okay, pi number 1, we take this one, right, and combine it with sorry, not this one. We take this one and we combine with our repeating variables. This is our repeating variables, right? If you look here, we have Z. This is our repeating variables number 1, repeating number variables number 2, right? W naught and Z naught. So the next pi 2, we can use this one and combine with this and this one. And the third pi, we use this, combine with this and this one. Okay. Let me put it down here. So pi 1, basically we use Z omega naught and Z naught. For pi number 2, we use T omega naught and Z naught. Pi number 3, we use G, W naught and Z naught. Of course, this one is the power of A1, B1. This one is A2, B2, A3, B3. Okay, that is the arrangement of that. Okay, because we already decide that this 2 is our repeating variables. Okay, so the non-repeating variable will be at the front. Okay? You can put it at the front or at the back, same thing. It will not change the solution. the answer. So for the pi number 2, as I just mentioned, you have a t, then you put together the other two repeating variables, which is w naught and z naught, and do the same process as what had been explained on the previous pi 1, and finally you will get something like this. Okay, pi number 2. And then for pi number 3, okay, you use the non-repeating variables g and combine with the repeating variables w naught and z naught, like so, and do the same process, and finally you will get this. Okay, okay, now you know that pi 1 is this and pi 2 is like this, and you also have pi number 3. Okay, and for the pi number 3, you want to uh, modify, okay, modify such that uh, uh, you don't want omega naught square, so you want to remove the square, so you basically you square root everything, right? You square root everything, and you rearrange. Okay, rearrange meaning that whatever at the bottom here, you move at the top, and the top going to the bottom. Okay, then you will get something like this. And when you get this, it is what we call Frucht number. Okay. And step number 6, write the final functional relationship and check your algebra. The functional relationship between the non-dimensional parameters. Okay. So basically, you can put your pi 1 is equal to the function of pi 1 and pi 3. Okay. It's like this. Or in terms of the non-dimensional variables, z and t, as we have already defined previously. Because this term we can, it is the Frucht number, or FR in short. So you can put it like that. It is our final result. Okay. And this is another example. Okay. Step on how to deal with flow of fluid. Okay. It is another example. The process is very much similar. Okay. And basically, on the last part, here on the pi number 2, what you will get is your Reynolds number. Okay. If you go to this example number 4, basically what we see is how we obtain our Reynolds number. Okay. And the last part here is the dimensionless term. Okay. There are a lot of dimensionless term. That here we have some of those. We have Archimedes number, aspect ratio, Biot number, bond number, cavitation number. Okay. Then we have Darcy friction factor, drag coefficient, Euler number, Fourier number, Frucht number that we have go through one example just now, right? Knudsen number, leaf coefficient, okay? Fractal number, pressure coefficient, Mach number that you have. I think you have know what it is, right? Okay. Then other thing, Reynolds number, and the rest. Okay. That is for chapter number 7. I hope you can appreciate what being explained from the these particular topics. Okay. And how we obtain that those dimensionless terms which is very useful for us to understand and how to correlate uh, 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 and know in physics and how it will behave according to their property. Okay, and to further look into the dimension and unit, of course. I hope with this knowledge you can expand whatever you have learned into something more interesting in the future. Okay, with that, thank you very much.